Tá bom, entendi.
Então, a gente entrando
Mas eu vou te
estou
ensinar
tentando
como...
entrar na sessão da tarde, é essa? É a sessão da tarde, como hoje de manhã era mini curso?
É porque
É, sessão da tarde.
Deixa eu ver se eu
Olha lá,
vejo.
deu.
Vê se você
deu.
tá na sessão da tarde.
Porque ainda não está me dando para entrar.
Então não deve ser aquela que você abriu, professor.
Não,
olha,
mas é que vai
tá
abrir.
certo. Não, o Zoom.
O Zoom. Qual sessão você está
Então,
entrando?
aqui, ó. Eu estou no Zoom. Você está
Mas qual
acessando
sessão?
via Zoom ou
Acho
via
que a sessão
YouTube?
de manhã, porque não é o
Vai no
mesmo
Santa
link.
aqui.
Não,
Então,
você que está... Você está sem conexão.
ele já tá aqui, ó. Tá aqui.
Eu acho que já deu.
Já apareceu, apareceu.
Mas eu não
Pode
apareci.
desligar. A transmissão tá...
Não, mas eu não estou. Eu preciso entrar também. Essa daqui, sessão da tarde, não?
Mas isso é o YouTube ou...
Não, o Zoom, eu preciso do Zoom, entrar no Zoom.
Não, mas é nessa que eu estou. Tem alguma coisa errada
É no mesmo link que você
contigo.
enviou.
Sim,
Não tá indo.
mas me deve aceitar, senão eu não posso entrar. Alguém deve
É
aceitar.
porque você não tá inscrito
Não.
no evento, seu e-mail, é por isso.
Ah, você não está inscrita no
Me deve
evento.
aceitar, me deve aceitar.
Não, sem estar aí inscrita, não.
Sim, eu entrei pela manhã no
Ué,
mini
estranho.
curso.
Então não sei.
Tem
Peraí,
que...
sai e entra de novo. O Vansan precisa de autorização para compartilhar. Tem que dar ele aí a autorização. Cadê?
Autorização, você dá
Faz
manhã.
ele ser host.
De manhã eu entrei. Eu preciso para poder enxergar.
Esse?
Você precisa entrar.
Isso.
Você me deixa.
Você apresenta aqui, e aí você deve.
Olha. Põe a...
Iniciou o compartilhamento. Então, na verdade, eu acho que é a internet. Porque, ó, Francisco iniciou o compartilhamento de tela.
Não.
Aí, viu?
Não, eu
Não.
posso botar no seu.
Não, sim, mas onde é...
Você foi treinado para ser transmitido igual os outros shows?
Sim. Ele ainda não compartilhou.
Tá bom.
Foi? Aqui não é isso ainda. É porque tem que esperar o compartilhamento. Ela tava na tela de carregando porque ele não compartilhou ainda.
Mas aqui?
Mas
não
é
está?
isso. É.
Mas não está ele.
Aí,
Cadê?
foi. Volta.
Cadê ele?
Tem certeza que esse daí é o de manhã?
Não, isso da tarde.
É. Aqui, mas ele...
Ele não está.
Então, na verdade, a gente pode
olha
descer com esse
Qual é?
computador.
Pode ver? Não, mas não é
Não
a
é?
sessão certa.
Agora, a gente pode descer com esse
Professor,
computador.
eu acho que o link do
Lá
Zoom tá
embaixo.
errado.
Hã?
O link do Zoom tá o de manhã ainda, eu acho. Tenta
Não,
botar no
eu acabei de
curso.
botar.
Mas a estação, ela tá no link certo e não tá aparecendo nada pra ela. Calma, deixa ela tentar de novo, gente.
Não, daquele de manhã ou daquele da tarde?
De tarde, tenta no
Não, mas espera, eu vou tentar daquele de manhã.
Tá no dia, certo?
Não, é primeiro dia.
Qualquer coisa que você tá no então, tá?
Ou então, porque é no YouTube que não está aparecendo.
É porque, tipo assim, ela tá entrando pelo link do mini curso.
Não, pelo link da sessão da tarde.
Qual é esse link? Você consegue ver o nome desse link do Zoom?
Não, mas não, o link de sessão da tarde é link do Zoom, do YouTube.
Não,
Não, é da sessão do Zoom.
Você não fez assim, só cada sessão tem um link. Você mudou o link do Zoom?
Não.
Você tá no primeiro. Não, olha lá. Afternoon Talks não mudei lá. Não, gente, ali tá no certo. Olha aqui.
Aqui está certo.
Aqui tá certo, Mariana.
Aqui está certo. A gente tem que... Tá certo.
Não, aqui tá certo. Pode começar, acho, gente.
Pode. Eu
Vai.
acho que a gente começa. A gente resolve o seu depois. Você não pode ficar sem conexão agora?
Aqui, olha.
É melhor ficar sem...
Afternoon Talks não veio lá. Tá vendo?
Eu entendo. Isso funciona tão bem? Nossa.
Meu microfone é esse.
Isso. Ele só vai ter que... Pode clicar adiante. Tá ligado.
Passar? Não? Posso apresentar? So, good afternoon. Welcome to the first plenary of our bio review. And I'm proud to present Professor Vincent Webb. He's such scientists work with model, mathematical model on statistical heat on Paris France. And now they give us the stock in doing clinical room through monthly models for physical biology.
Thanks a lot. So thank you everyone for coming, and thanks a lot for the invitation to present my work here. So today I'm going to talk to you about my work, which is on modeling of biological system, which is starting to go towards what we call digital twins. So I will present also this concept to you. And so, like Alexandre said, I'm a researcher at Institut Curie in Paris, and I'm now living in São Paulo and starting to move long-term to Brazil. So I will start by introducing you quickly what I call multi-scale modeling of biological system. Then I will introduce you what we use for to model signaling, which is continuous time Boolean modeling with a software we call MADOS. Then I will show you the tool we are using that we developed to be able to do this multi-scale modeling, which is called CCLOS. Then I will show you one example of model that we published on the different modes of consigned cell intelligence. And finally, I will show you the ongoing projects I'm working on right now. So what do I mean when I say that my work is trying to go towards what we call digital twin? So basically, with the advance of data gathering and diagnostic, we are able to get more and more data about individual patients, and this at different scales. We are able to get clinical data about what's happening in a large scale of the body, but we are also able to go really deep and get some information about what's happening inside some particular cells of a particular patient. So the idea long term is to try to exploit this data, to use it to adjust some generic model of how our body is working, so that we can get a model which is patient-specific. So this term digital twin, which is kind of a buzzword these days, basically just means personalized models. So it's nothing that fancy. But still, we believe that this is something which is really important, so that we can get really some personalized diagnostic about patients, some personalized idea about the progression of particular disease pathologies, and most importantly, trying to get some personalized treatments which apply mainly to specific patients. So also one point I want to make is that we shouldn't think of it as one huge model which represents the whole body. For most pathology, we don't need to go into that much details, and this is something which is maybe completely just impossible to achieve. What we should focus on is on simple systems which involve, for example, just one or two organs, which are really specific to a pathology. We need to move on from the step, and basically try always to think small but useful. So this type of problem is what we call a multi-scale problem, because many parts of the regulations are happening at different scales of the body. You have a huge part, and for example, Alexander talked this morning about many parts of signaling, which are very important, which are the inside cells. But we also have a large part happening in the coordination, the organization of cells, in how cells interact with each other. Then, at another level up again, we have an organization of the tissue as really a special organization of different cell types coordinated together. Then we have a level of organ, and finally, the whole body. So basically, what I want to show you today is the work we are doing, which for now mainly encompasses these two first scales, and starting to go toward the tissue scale, where we really have some kind of special organization of cells in the tissue. So first, the cellular model, I won't go into much detail on this, because I think the course is mainly focused on this, and Alexander did already a report this morning explaining it. So this is the part of modeling of computational biology which is the most unique, which is all which deals with signaling, which is a huge, complex machine. There are many different frameworks that we can use for this. So one framework would be quantitative. So for example, ordinary differential equation, which is something that we show, that Alexander showed this morning. where value can be any quantity. We have a notion of continuous time, so we can ask for the state of the system at any given time. The problem of ODEs and of quantitative frameworks is that these systems are difficult to write, even more difficult to parameterize. And also, if we want to simulate a very large system, thinking in the hundreds or the thousands of variables, we have a big computational problem. On the opposite side of the spectrum, we have a type of framework which is more qualitative. For example, Boolean frameworks, where values, for example, are just true or false. Thinking of the analogy in biology, they are absent or present, they are active or inactive. There are many variables where this simplification makes some sense. One limitation of biological Boolean models is that we don't have a real notion of time in pure Boolean models. We just have a notion of sequence of events. We know that this happened and then that happened, but we don't know about the time happening in between. Positive sides of this type of framework, they are really easy to write. They are very close to natural language. So, for example, we can say that to have this behavior, we need that. And also, they are useful because we can simulate very large models. By large, I mean hundreds or thousands of variables. So one quick example of Boolean formalism for people who are not used to it. So let's take a very simple system with just 3 variables. A is not influenced by B or C. So A is fixed at the beginning of the system and won't move during the simulation. B is positively influenced by A, meaning that A will activate B. And then both C is inhibited by both A and B. So how do we write this in a Boolean framework? The formula of A is non-important, but in this case, since it receives no influence, we just put A. B only receive influence of A, so the formula of the variable A will be B will be just A. And the formula of variable C will be either A inactive or B inactive. Very simple to write, makes sense when you look at the graph. Then for initial values, we'll take some very simple initial state where A is active, B is inactive, and C is active. So what will happen is that first we will have B activated because B is activated by A, and then C will get inactivated because B is active. So this is very simple, but still useful. But still, in the lab I'm working in quantitative theory, we wanted to go a bit further than this and to add one notion which is really missing in Boolean modeling, which is time, the notion of physical time. So Gauthier and Laurence developed a framework called MABOS, which uses what we call continuous time Boolean modeling. The idea basically is that we add a notion of physical time to every transition. So remember I told you that Boolean models, you just have a sequence of events, but no notion of time between 2 events. Here basically we introduce some kinetic rates which will be able to give you the time which happened during these 2 events. Some very basic example of how does it work. Basically, the formula we define are either activation or inactivation rates. So for A, we already told you in the last example, A is not influenced by nothing. So A won't be activated and won't be inactivated. The rate is 0. For B, we use this kind of formalism called ternary equations, which basically is some if-then-else. If A is active, then the rate of activation will be 1, otherwise it will be 0. So basically when A is active, we will have some probability of B to become active with time. For the inactivation, it's exactly the opposite. So if A is active, then probability to inactivate it is 0, but probability to, if A is inactive, then probability to inactivate is 1. And we have something similar for the C variable. What you can see also here is that the rates of B and C are different. B will be faster to activate than C. And this we will see in the example I'm going to show you now. So we take the exact same initial values. And what we obtain with MABOS is trajectories of state probabilities. So at first we start with a state where only C is active. Then very quickly B will become active too. So we enter a state where both B and C is active, which is the red state. And then variable C will start deactivating, but more slowly. And then we enter a state where only B is active. So this is when we look at the states, like we have coexistence of B and C at some point. But we can also just simplify it and just look at the variables. And you see that B activates very quickly and then C inactivates more slowly. And what we also, most of the time, what we look at with this type of model are just what's happening at steady state. Not exactly steady state, because we simulate for a given time, but we make approximation of steady states. And here, if you look at the long term, most of the states will be only B active, and you will have some small parts, if you don't simulate long enough, of B with C still inactive.
Acessa a internet de graça, cara.
So a quick example of this on a more applied model. So here is a simple model of TNF and fast action on cell fate. So here I will mainly focus on the effect of TNF on the cell fate, where basically when we activate TNF, it will either activate survival, the cells will survive the TNF treatment, non-apoptotic cell death, non-HCD, which is some kind of necrosis, or apoptosis. And so when we don't activate TNF as an input node, what we get is some kind of quiescent state. The cells don't die, but are just there in homeostasis. But when we treat the cells with TNF, when we activate the TNF, we get a proportion of 90% of the cells triggering apoptosis, 5% more or less triggering necrosis, and 5% triggering survival, meaning that the cells survive the treatment, which, by the way, is caused by NF capability. When we do the exact same treatment of TNF on the wild type cells, you get the proportion I just showed you. But what is interesting with Boolean network is that we can also very easily do mutations. And for example, we can force the activation of IKK and simply inside our Boolean network. And when we do the TNF treatment, what we get are cells which are completely resistant to TNF. And of course, it's still a continuous time framework, so we can also look at the trajectories of all these behaviors in space. And this will become more important in the next part of the talk. So also one part, important part is that we work very hard to make this easy to use our framework. So one of the first things, for example, that I did arriving in theory is to develop some web interface where you can just connect and start playing, building models, simulating models, and getting quick results without having to know everything about development. One other possibility is to use Python. So we have also Python bindings, a library called PyMabos, where we can very easily load a model, simulate it, and look at results. And finally, we also develop a framework called Profile to be able to personalize these models. So what we do, we take some generic logical model, we take some omics data from patient or from cell lines, which would be, for example, list of mutation, copy number alteration, RNA-seq. We are working on single-cell RNA-seq right now. And with this data, we are able to personalize the model, meaning adjusting the inactivation rate, adjusting the initial states of the model, and we are able to generate patient-specific logical model. And with this, for example, we are able to personalize according to different grades of cancer and show that the more advanced the cancer, the more proliferative and the less prone to trigger apoptosis. So just a quick summary of this first part of MABOS. So it's a very simple yet powerful tool to model signaling. It is stochastic, like I showed you, that we can have a distribution of different outcomes for the same treatment. And so it allows the description of heterogeneous behaviors. There are simple ways to get started, either through a web interface or from the Python bindings. We can handle some very large model. One part of the work I did in the last years was to adapt it so that we can use big computer clusters to simulate very large model. We also just published a version using graphic cards, GPUs. And also, more importantly, MAPOS is more than pure Boolean model because we add a notion of physical time, which is something which is lacking to the basic Boolean models for many applications in biology. So to go back to this image, I basically showed you now what we are doing for the simulation of cells as agents. But now I want to go to more advanced, larger scales where cells communicate and interact with each other and maybe organize themselves into tissues. So for this, what we want to do is to model some multicellular systems, so many cells together. For example, here is a simulation of a tumor with many cells, many tumor cells in a yellow to blue color. Each cell has spatial information, each cell has a position, a list of neighbors with which it can interact. We can have multiple cell types. In this case, for example, we have the tumor at first, and then we have the red cells, which are immune cells arriving to kill the tumor. We also have a notion of extracellular environments. You can see in the middle of the tumor, you have some brown cells and also some holes. These are the cells which lack access to oxygen because most of the oxygen was consumed by the periphery of the tumor. And so these cells are triggering necrosis and dying of lack of oxygen, basically. And finally, the cells can interact with each other and, for example, try to kill each other. To do this kind of model, we are using a framework called PhysiCell, which is an agent-based modeling framework. So the basic idea of agent-based modeling is that you can define agents, in this case they are cells, and you give them some specific properties such as size, volume, notion of phenotype, what kind of cell cycle they are using, are they growing, are they moving in space, how can they interact with other agents. And then you just create many of these cells, you put them all of them together and you see what happens. This is a basic idea between agent-based models. Like I said, you also have a notion of microenvironment. So here you also have a grid where you can have many types of molecules diffusing, interacting with cells, being secreted or degraded by cells. And what we did with PhysiBoss is that we added MAPOS, so the continuous time Boolean models framework I introduced you earlier. We added it inside each cell. Because in the basic framework of PhysiCell, each cell is kind of dumb. You cannot do many complex things with it. You could in theory, but then you would have to go through a lot of C++ code, which is not for everybody. So what we wanted to do is to put this type of Boolean models inside each cell so that all the signaling parts of the cell will be computed by this Boolean network. And for example, a cell, according to the conditions, to its condition, will decide if it should proliferate or trigger apoptosis. So how does it work? It's very simple. We just take every cell regularly. We look at its surrounding, at the signals that the cell is perceiving. For example, it sends some oxygen nearby, or it's in contact with another type of cell. This will inform us to which kind of initial state we should put our signaling model in. Then we simulate this Boolean model, and according to the output of our simulation, the signaling will decide if the cells, for example, should survive, proliferate, or die. After a lot of work, at first this framework was just pure C++. You had to know how to code in C++ to be able to do any kind of model. Then with time we migrated to some configuration files to be able to define a model. And nowadays we just publish a graphical interface, so you are able to build this kind of models only clicking buttons and filling fields inside the graphical interface. You're able to simulate your model and you're able to explore any part of the results indirectly inside the graphical interface. So the process of model development just got a lot simpler. I will show you now one example of such model. So the idea is to simulate the effect of TNF, which is the model I introduced you before for my boss. Simulate the effect on the population of cancer cells. This was one of the first models that was developed with PhysiBoss in his time, where PhysiBoss was just a proof of concept. And we basically wanted to rebuild it completely from the ground up, using our new system and our new graphical interface to see if really it was easy as we thought to build this model. So we take this Boolean model that I already showed you quickly, which without TNF just stay in homeostasis, but with TNF will mostly die of apoptosis, bit of necrosis, and some will survive. And basically we just take in our agent-based a population of cells which are proliferating. We link the detection of TNF by the cells to the initial states of TNF in our Boolean model. We linked the phenotype, the output of our simulation of a Boolean model, to the rate of apoptosis and the rate of necrosis to be able to trigger this. And basically, then we just have to simulate it. And we see that at first, most of the population die, like I showed you earlier, around 5% only survive. But then, very quickly, this 5% will continue proliferating and will form a new tumor, which is resistant to the treatment of TNF. One interesting aspect about this Boolean model is what happens when you do pulses of TNF. When you put TNF, when you remove it, you put it again, you remove it again. Here you can see the gray area are the parts where TNF to try to provoke metastasis, basically. So here, there are one interesting aspect of this is that we can have several ways by which these cells are leaving the tumor. To make it very simple, you can categorize them into two ways. Either the cells will leave alone, one by one, the tumor. In this case, it's not a big problem because cells alone like this in the tissue will most likely die. But you also have another behavior where cells will move together as clusters, and then these clusters of cells, of cancerous cells, will have more risk to provoke metastasis. So what we wanted to do is to develop some basic multiscale model which would try to see what are the important aspects which are influencing these two behaviors. And how can we, for example, try to prevent too much collective migration and to have more single-cell migration, which is not as dangerous. So here you see on the right the type of simulation we are doing. So we have our initial tumor. Around these small boxes are a simple representation of the extracellular matrix. So cells will sense the extracellular matrix and will activate degradation of this extracellular matrix and will basically dig some tunnel inside the extracellular matrix to be able to leave the tumor. Inside each of these cells, we have this Boolean network, which is one still very simple, around 30 variables or so. Basically, we have 7 input nodes, so we can detect the presence of oxygen, of growth factors, of TGF-beta, which is trapped inside the extracellular matrix. We can also inform the presence, the contact of cells with the extracellular matrix or with other cells. And also we can represent the DNA damage caused by the cells being crushed against the cellular matrix. And by informing all these different input nodes, we can simulate some behaviors, which would be, for example, the cells will be pushed to proliferate, will be pushed to adhere to the extracellular matrix, and maybe further start to degrade the extracellular matrix. The cells will start to migrate in the tissue and will leave the tumor. The cells can also just stop where they are and not do nothing or die of apoptosis. So what we were able to do with this type of model is, for example, to reproduce some known experiments of activation of the SARC oncoprotein inside the tumor. So that what biologists did here is that they took some cancer cells and they just flashed a blue laser on them, which activates, thanks to a biological construct, activates the SARC oncoprotein inside each cell, which is flashed. And so here we see that the cells have SARC active and start immediately migrating. And after some point, they can just switch off the laser and the cells will go back to the state where SARC is inactive. Some cells will have left the tumor already, but most of the cells will go back to their naive state. And this we were able to simulate this exact condition inside our model and show that we get the exact same behavior. Once our model was validated, we did a bit more validation, but I'm not showing here in the interest of time. What we wanted to do is to play with the model and to look at which parameter would provoke more or less of this single or cluster migration. So we did a big parameter sensitivity analysis on a big computer cluster. This takes many computing resources to be done, but this is the kind of important thing that can be done with this type of model. And for example, we are able to see that one of the variables of our model, which is the migration bias. So when you have a cell which is attracted by a gradient, which is following a gradient of some chemical, the bias will be how much stochasticity is there in its movement. Is the cell going straight toward the gradient, or is it just wandering around more or less in the direction? And here we see, for example, that when the migration bias is high, when the cell is very efficient in following these gradients, we have more single cell and less cell cluster in proportion. What is that? Can I just print? No, it's back. Okay. So, sorry. Okay. So yeah, it's in proportion, we have more single cells and less cells moving as a cluster, but actually in quantity, I think the battery is dying. So I can just finish screening maybe.
Let's try.
This one.
Yes.
So I can-
I switched it off. I switched it off. Okay. So again, just to briefly repeat the conclusion, here we can have more cells as a proportion living by themselves, but as an absolute value, actually, we have more migration when these cells are able to better follow the gradient. So this was published last year, and so we are able to reproduce this early state of invasion. Inside the tutorial that we are trying to publish right now, we have an updated version of this model, which uses a lot less C++ code and a lot more of this automated way of building models. And we still have a lot of room for improvement and validation of this model. For example, we are also trying to add a mechanism by which cell will settle to new tissue and stop this migration. And just to finish now, I'm going to show you the ongoing project. So my main focus now that this software is more or less done and robust, we want to build more models and we want to focus mainly on one part, which is cancer-immune interaction. So the first project that I'm working on right now is a European project called Certainty. And the idea is to build this kind of virtual twin for CAR-T treatment therapies in multiple myeloma. And the idea will be to, for each patient, according to all the data gathered on a specific individual, to be able to propose patient-specific tailored treatments. And for this, we use both a statistical approach, which is basically taking all the clinical data, but also a mechanistic model, which is the type of model I just presented, to be able to inform and to try to find the best treatment. The other project that I'm going to start soon is a collaboration with Thiago Medina at AC Camargo around what is called tertiary lymphoid structures. So basically, these TLS are a special organization of immune cells in close proximity to the tumor. Basically, what happens when you have a tumor usually is that you have macrophages detecting the inflammation, provoking inflammation, detecting the problem, and trying to recruit immune system. But for effector T cells to be able to attack the tumor, dendritic cells have to go toward the lymph nodes, activate naive T cells there, and the T cells will go back to the local of infection or tumor. TLS basically is a shortcut of this. Basically, in this case, some patients are able to develop some kind of mini lymph nodes just next to the tumor, so that we can have production of effector T cells able to kill the tumor just next to it. And this has been shown, Thiago has shown that in multiple types of cancer, this is a predictor of response to immunotherapy. But the patients which have this TLS have shown better results to immunotherapy treatments. And so it's still a big unknown. We don't know why some patients have them or not. We don't know exactly how they are formed. And if we could understand how to trigger the formation of these structures in many patients, we could in theory improve the success rate of immunotherapy. And we think that this is the kind of model which is a good fit for Physibus because it deals with interaction of many cell types and spatial organization of cells together. And so if anyone is interested about this or knows somebody who would be interested in working with me to build such kind of model, please let me know. I'm looking for a student. And finally, the last project that I will start very soon is a project about T-cell explosion, which is mediated by cancer-associated fibroblasts. So here, the basic idea is that for many tumors, you will have infiltration of T cells inside the tumor to be able to effectively kill the tumor. But in some cases, you have another type of cells called fibroblasts, which will form a barrier around the tumor, basically preventing the T cells to enter the tumor and kill it. we don't know yet exactly why and how these barriers are formed, and how, like, the most important thing to find out would be how to break this barrier, how to disable it, so that the T cells are able to reach the tumor. And so we are working with Hélène Salmon at Institut Curie, who just built some spatial transcriptomics datasets on this topic. And we are starting to build some methods to be able to create models based on spatial transcriptomics datasets, which will be already personalized. And for this, we already have the students starting in January. And so just to conclude, we believe that this kind of multi-scale models are important to describe multicellular systems. I think especially important if we think about cancer-immune interaction. And also with systems which has some special properties, like I just showed you about the TLS or the T-cell exclusion. We believe also that adding this intracellular layer, this Boolean layer inside our cells, allows us to simulate easily the type of treatment, the type of modification in signaling that's happening, either due to mutation or treatment. And so it's important to be able to have personalized treatment. Physibus, so our framework to build this kind of model, is getting simpler, and we are now focusing on building more models, and also on developing new methods to be able to use data to be able to adjust this type of model. And I'm actually already now living in São Paulo, and I'm looking for students and collaboration. So thanks a lot for your attention. And thanks a lot to all the people who did the work. Most of the work was done by Marco Oscone, just defended in our lab, and his name Barcelona. Thank you.
Thank you, Doctor. So now we will turn over for questions in the audience. You can share there.
Yeah.
Okay. So any questions?
Dr. Wilson, thank you very much for a very nice talk. Second time I've seen it. Very good again. Fabrice Alves, one of the organizers, is asking here in the Zoom chat. Is asking, does Physibus scalable to simulate a whole organ like the liver today? Possibly.
Today, no. We have some work with people from Barcelona, like Arnaud Montaigu, Miguel, Alfonso Valenza, to be able to make it scale up. Like for now, the part of Mabos runs very smoothly and doesn't need much. The agent-based part is still limited. And we are working for now 4 years, and we are still making new improvements. And I think that the biggest we were able to simulate in Barcelona would be 20% of the liver or something like this, which would be hundreds of millions of cells. I'm not exactly sure about the figures, but yeah, it's not yet working. We are working towards it, and actually, postdoc will arrive there at Barcelona to try to improve this even more, to have basically various instances of PhysiCell running on multiple GPUs and communicating with each other. So it's work in progress basically, but we are really trying to do it.
You mean Barcelona supercomputing?
Yeah.
Okay. Nice.
Well, like all this Physibus collaboration is basically between the lab of Alfonso Valenza in Barcelona, our lab in Curie, and Paul McLean's lab, which are the original developer of PhysiCell.
Sorry, who is the one from Barcelona? Who is the one from Barcelona supercomputing?
Alfonso Valenza.
Oh, okay.
And Paul McLean is the leader of development of PhysiCell in Indiana University.
Very nice work. I think it's very useful, but I think the signaling network is very complex. You have to find And the question is how to what's the best choice? What do you do to choice this one or better than lower? Okay, and then to compare with the experiments, this is a guide. But can you talk a little bit about that?
I think this is still a completely open question. Like we don't know exactly for which. We know that in some cases, really we don't have just active or inactive states for a specific protein. We need to have a lot more information about the exact quantity and many different states. With Boolean, we can still cheat a bit and have, for example, multiple levels for one variable, and it's not just active or inactive. It can be, for example, half active, but still for some components of the signaling, we need to have real continuous value. So I think this is still something which is open, and we always try to make it as simple as possible because for us it's better, and because computationally also it's better. But basically we need to get stuck somewhere, not being able to reproduce the model, the results, I mean, and modify our model to add some continuous variable to show that this was the missing piece of the problem. So I think it will be just trial and error, which would show us what really is needed for this type of question. And by the way, here in the framework I presented you, Physibus only has Boolean models inside, but together with other people at University of Indiana, with Paul McLean's lab, we also are adding the possibilities of having differential equations inside each cell. And we are working towards having some kind of mixed model for signaling. But this is beginning. Hello.
Very nice, sorry. So I was wondering, how can you predict if someone would be able to form these tertiary uniform structures? I mean, let's say basically their in-system would be possible to predict. Let's say if someone has more lymphotoxin or, you know, cytokines that we know play a role in differentiation of secondary lymph nodes.
No, I think we are still a long way to get there, to be able to predict. But I think that the exercise of building the model will help us understand a lot more mechanistic details about this TLS and what are really the specific factors which favors or prevents the formation of this TLS. And so I think that at some point we'll be able to predict. But I think that indeed we are very far from it. But the process of getting there will teach us a lot about what is preventing or what is impossible or possible. But no, I still think that one day we'll be able to predict it and to try to find actual clinical action to be able to trigger it.
Any more questions?
I have one. So, these tools you are describing, are they, what kind of parallel computing they support? It's 4-level, cluster level, GPU level, are they already ready to be used to develop?
So like I was saying, we are working toward it. Today, if you take Physibus, it's working in parallel at the thread level, so using OpenMP. So on your machine, if you have 20 cores, you can use the 20 cores. We have some prototype version of MPI, so working on different machines inside the cluster, which is not finished yet. We also have a prototype of GPU version, so working graphical processors, which again is not finished yet, but we have this postdoc arriving in Barcelona with the best C++ coder I ever saw, who wants to mix two of them and to finalize them. So we'll be able to have things running on various machines and various GPUs to be able to simulate very large systems.
And why is C++? Why is C++?
Because like if you want to do very complex things and to have them very efficient, I think this is still the best language that you have. Like Python will be limited, and for example, for Mabos, we are using Python, but when you use Python, what is actually doing the simulation is some bits of compiled C++ always. And we haven't tried other language like Julia or something like this for now because it's just start to do C++, so we go with it.
Thank you, Wilson. Another question? No? So we are going to change a little bit the schedule. Now we're going to make a coffee break, and afterwards we return with Professor Gilson. Okay? So we'll come back soon. Thank you.
Como não vamos São Paulo? Eu gosto muito. Tá, bom. Isso é uma coisa que ainda precisamos fazer muita coisa. E mesmo boa grande parte desse trabalho vai ser feito para esse pós-doutoral superior, que ela é um gênio. Mas ainda vai ter coisas mais para fazer por lá. Não, seria bom isso. Ei. Todo mundo percebe.
Poxa, que é um e-mail.
Não consegui. Vamos ver aqui. Faz assim. Se ele isso é importante para você, tá? Segurar e tal. Você não vai sofrer mecanismo, ele vai ser como os exatamente, ele vai ser melhores. Isso é uma macrófago, dependendo das características celulares. O estado perde certas características eu espero que tenha. Você almoçou por aqui? Estamos aqui perto. Aqui foram caminhando. Não. Não, foi de carro, foi no antigo. Eu vou esperar o nome, é o nome de uma. Não sei. Tem uma coisa aqui da parte do corpus que tem suplências. Sim, você não pega isso. Aqui tem pertinho, não é tão bom. As áreas pararam, tem um que é pertinho e muito cheio. Esqueci nada. Aquele do lado é seu. Muito bem. Você fica até hoje? Até amanhã. Você vai ficar aí? Eu vou dormir aqui. Não. Deixa eu pegar uma.
Vamos
O
lá.
dele, pode dar uma olhada no dele primeiro, que é mais importante.
Nossa Senhora. Onde? Eu não sei onde vão ter botado. Tem que procurar quem organizou isso aqui.
O dele, pode dar uma olhada no dele primeiro, que é mais importante.
Nossa Senhora. Onde? Eu não sei onde vão ter botado. Tem que procurar quem organizou isso aqui.
Eu preciso baixar, né, a apresentação. Onde que eles estão?
A apresentação, dá uma olhada no dele primeiro, mais importante.
Nossa Senhora. Onde? Eu não sei onde vão ter
Já vão baixar
botado.
todas lá, para você um em sequência da outra, as apresentações?
Ah,
Procurar quem organizou isso aqui.
deixa eu ver. Eu preciso baixar, né, a apresentação. Onde que eles estão?
A apresentação, dá uma olhada no dele primeiro, mais importante.
Nossa Senhora. Onde? Eu não sei onde vão ter
Já vão baixar todas
botado.
lá, para você um em sequência da outra, as apresentações?
Ah,
Procurar quem organizou isso aqui.